Now let's get very concrete and practical. In the following short series of lessons, we will discuss different statistical tests, in which scenarios they apply, which conditions need to be fulfilled for these tests to be valid, but also which questions they answer. For instance, based on the sample dataset that you are given, is the underlying population a normal distribution? Or, based on the two samples that you're given, do these samples come from populations that have equal variances? Or yet another question, based on the two samples that you have, do the underlying populations have equal means? Which is of course the scenario that we looked into much detail in the previous lessons. Or even better, do these samples come from the exact same population? Now all of these questions, they have in common that they are questions about the populations based on your sample dataset. However, all of these questions are different because they revolve around different statistics. We have, for instance, the variance, the means, but also about the distribution function of the populations. Now, because these questions all revolve around different statistics, they will also need different statistical tests to formulate an answer. Now, what does it mean to be a different statistical test? Well, as we saw, the basic idea behind a statistical test is that you compare your observed sample statistic with an underlying distribution of sample statistics. Now, this distribution, in our case, where we compared the difference in sample means, was this approximate normal distribution, and in reality, a student t-distribution. But this specific distribution is only valid for the case where we compare the difference between sample means. If you, for instance, want to compare the difference in variances, then you would need a different distribution. So each statistical test revolving around a different statistic that you want to investigate, you will need a different distribution. Now, additionally, all of these different statistical tests require different conditions on your dataset to be fulfilled. For instance, some statistical tests might require your population dataset to be a normal distribution. But what is very important to realize is that even though we have different statistical tests and thus different of these underlying distributions to compare our observed sample statistic with, what remains the same for all of these tests is the underlying reasoning, which is why it is very good that we already covered this underlying reasoning in great detail in this chapter. Now, in the following lessons, we will devote each lesson to a different statistical test. And we start with the test that is most often used because it looks at a property of our data that is a requirement for all of the subsequent tests. And this is testing for normalcy. So the scenario is the following. Let's say that you're given a sample data set and you need to find out whether this sample data set comes from an underlying population that itself is normally distributed. Now, because testing for normalcy is so important, we will look at a couple of different tools that allow you to make this conclusion. They will be both visual tools and numerical tools, of which the p-value is of course 1. But let's first look at an example. What you see here are the histograms of two samples. One sample comes from an underlying population that is normally distributed, and the other sample does not come from a normally distributed population. Now, by looking only at these histograms of these samples, can you determine which one is the normally distributed one? Well, it's indeed very difficult to do. And in fact, it is the left sample that comes from a normally distributed population. So which tools then do we have to actually make this conclusion? Because clearly, just by looking at these sample histograms, we cannot do this. And the first tool is of course the statistical test itself, which for checking for normalcy is called the Shapiro-Wilk test. Now this test will again provide you with a p-value, and the underlying null hypothesis is that the underlying distribution is indeed normally distributed. Now this of course means that if we have a large p-value, then we accept the null hypothesis and we conclude that the underlying distribution is a normal distribution. But if we have a low p-value, then we reject this null hypothesis. So let's see, for instance, what the p-values are for, again, these two sample distributions, of which only one is from a normal population. And indeed, if we compute the p-values for these specific samples, we see that on the right side, we get a p-value of 0.71. And thus, clearly, we can accept the null hypothesis, meaning that this sample is very likely to have come from an underlying population that is normally distributed. Whereas on the right side, we get a p-value that is 10 times lower. And thus, in this case, we could reject the null hypothesis, depending on our statistical significance level, and therefore conclude that this sample is not drawn from a normal distribution. And again, because we generate the data in this course ourselves, we can just check our results against the underlying populations from which these samples were drawn. And we see that indeed, the left sample came from a normal distribution, whereas the right sample came from a uniform distribution. And this shows that we can just use one statistical test, which in Python is one line of code, which we will see shortly, to compute the p-value to check for normalcy. Now, there is also another way to check for normalcy, namely the QQ plot, which is partly a visual approach, but then also again has a numerical value attached to it. So what does this indeed show? In the QQ plot, we compare the percentiles of our specific sample dataset with the percentiles of a theoretical normal distribution. And thus, if we see that our percentiles are in agreement with the percentiles of a normal distribution, then we can conclude that indeed our sample is normally distributed, or its underlying population is normally distributed. Concretely, on the x-axis, the horizontal axis, we have the quantiles or the percentiles of our theoretical normal distribution. And on the y-axis, the vertical axis, we have the percentiles of our sample dataset. Now, these are just, of course, the ordered values of our sample dataset. Now, because we plot these two percentiles against each other, the more that they are equal to each other, and thus the more our sample dataset resembles a normal distribution, the more our sample points, which are these light blue points, will lie on this black line right here. In fact, if we had a perfectly normally distributed sample dataset, then all of the points will lie exactly on this straight black line. Now we can compare the two, for instance, and see that on the right-hand side, our sample points are much more closely aligned with this black line. Whereas on the left-hand side, we see that they are not that aligned. So from this visual inspection, we would conclude that the right sample is the one from a normal distribution, where the left sample is a sample drawn from another distribution. Now, this is of course just a visual inspection. If you want to have it more precise and thus get a numerical value for this, then we compute the r-squared value for each of these plots. Now, the r-squared value is basically a measure for how closely clustered around this line our sample points are. And the more they are clustered around this line, the higher the r-squared, with a maximum of 1. And we see on the right-hand side that we have an r-squared of 0.988, very high. Whereas on the left-hand side, we have a significantly lower r-squared, just about 0.9. And thus this QQ plot and the corresponding r-squared metric are an alternative way to check for normalcy of your sample dataset. The last tool that we will look at is again a very visual tool, but one that you can very easily understand. In this case, we compare the cumulative distribution function of our sample dataset with one that is generated for a perfectly normal distribution. Here we clearly recognize this black S-curve being the cumulative distribution function, which is typical for a normal distribution. And thus, if we also plot the CDF for our sample data, we can see how well it matches with the theoretical one for the normal distribution. On the right-hand side, we see that it quite closely follows this theoretical line. And thus we can here very clearly see that our sample is also distributed according to a normal distribution. Whereas on the left-hand side, we see of course that, well, our sample CDF is not near our theoretical normal distribution CDF. And thus this is another clue that our left sample dataset is not drawn from a population that is normally distributed. And thus, we have now 4 tools to check whether our sample dataset is drawn from an underlying population that is normally distributed. The first one is the sample histogram. However, this is a very unreliable tool to check for normalcy, specifically when our number of sample data points is small. The second and most reliable tool is to look at the p-value coming from the Shapiro-Wilk statistical test. Now, this only requires 1 line of code in Python and it spits back a number. And you just check if this number is larger or lower than your statistical significance level. The null hypothesis in this case is that indeed the distribution of the underlying population is normally distributed. The third tool is the QQ plot, or the percentile plot, together with the R² value to give it a numerical metric. The higher R², the more likely it is that our sample comes from a normal distribution. And this corresponds to these sample dots being close to this black line. And then the last tool is to compare the cumulative distribution function of your sample dataset with the one generated for a perfectly normally distributed dataset. And the more they overlap, the more likely it is that your sample comes from a normal distribution. So let's now see how we can implement all of these 4 tools in Python by going, of course, to our trusty Jupyter notebook. The first thing, as we always do, is to define the number of population data points, which we then use to generate a population. Let's first generate a normal population. So here we know that our sample will indeed be drawn from a normal distribution. But as you can see, I have some other populations lined up here that are not normal, namely the uniform and the exponential distribution. Then we define a sample dataset, in this case with a sample size of 20 data points, so quite low. And then comes the 1 line of Python code that computes the p-value for the corresponding Shapiro-Wilk test, which is the statistical test for testing for normalcy. If it's a large p-value, then we accept that the underlying distribution is normally distributed, but when it is a low p-value, we reject this null hypothesis, and we can print this p-value. Now, to look at the visual tools that we had, we first of course create our figure and our axis. In the first panel, we plot the histogram of our population. In the second panel, we plot the histogram of our sample, and then we come to the QQ plot. Now, to get all of the information that we require to plot the QQ plot and get the R² associated with it, we do the following. We define 2 new variables by stating stats.propplot. We give it our sample, then we give it the distribution against which we want to compare it. In this case, we want to compare it with a normal distribution, and then we give it the axis on which we want to plot it. In this case, the lower left panel of our subplots. And this already takes care of the plotting. Now, the R² value comes from this variable right here, which again is unpacked, and it gives the slope of this black line, the intercept of this black line, but also the R metric. And then the R² we get, of course, by squaring this R metric. And then we can print it and give our panel some nice layout. Then the last tool is, of course, to visualize the comparison between the CDF of our sample and a perfect normal distribution. Thus, we first compute the CDF of our sample, which again requires 2 arrays, and then we compute the CDF of a perfect normal distribution. And this perfect normal distribution is defined directly in this sort function. And then we give our plot some layout. Now, if we run this, then we see that we indeed get all of the figures that we want. We get a p-value for our Shapiro-Wilk test to be 0.91, which is very high. So already from this, we can conclude that indeed our sample comes from a normal population. And the R² is 0.98, also very large, which we can also see because these dots are centered really well around this black line. And also our cumulative distribution function is very close to the theoretical curve. Now, of course, this changes if we, for instance, change our population. Let's say that we now draw a sample from a uniform population. And let's see what we then get. The first thing we see is that the p-value for our Shapiro-Wilk test is quite small. It's 0.078. Now this is not small enough to actually reject the null hypothesis in the case that we take a typical statistical significance level of 0.05. But that is why we have other tools to also check for normalcy. In this case, we see, for instance, that our R-squared value is quite small compared to what we had before. Before we had 0.98 and now we have 0.93 or 94. And indeed, if we look at our QQ plot, we see that these points are not exactly following this black line, which is also the case when we compare our CDF functions. Well, clearly, this blue line, which represents the CDF of our sample, does not follow this nice theoretical smooth curve at all. So these visual inspections and the R-squared combined with such a low p-value allows us to nonetheless conclude that this sample is unlikely to have come from a normal population. Of course, we can fix this p-value because we prefer to be able to make a conclusion solely based on the p-value by, as always, increasing our sample size. Let's say, for instance, that we increase it, well, not too dramatically, but just to 50 and see what we then get. In this case, we do indeed see that the p-value is low enough. It's 0.02, which then allows us to reject the null hypothesis. And in these cases, and in fact in general, the p-value will always be the primary tool, and it will trump other tools if they disagree. For instance, here we see that the R-squared value is in fact higher than we had before. And indeed, we also see that these points are more aligned with our theoretical black line. However, if we, for instance, increase the number of samples even more, let's say to 500, then we see the p-value plummet even further, which is the best evidence that we have. Now, you can also change the population to an exponential distribution, just to end off this lesson. And we also see that the p-value is incredibly low, and thus we can already reject the null hypothesis. But also the R-squared, in this case, plummets very fast. And we see, of course, visually that these points do not at all follow this black line. And also that the cumulative distribution function, well, is way off. And this is how you test your samples on normalcy. Now, in general, you will only need one line of code, namely computing the p-value for the Shapiro-Wilk statistical test. And that is in fact what we will do in all of the following tests, because they will all have as a requirement that the population of our sample will be normally distributed.